In this video, we are going to go over some examples from sections R2 and R3 from our textbook, and that is polynomials and factoring. So the first thing we'll look at is an example for adding or subtracting polynomials. So we'll start with we're going to subtract these polynomials, and these are actually called trinomials because we have three terms. And the first thing that we want to do is distribute this subtraction to each term. And so we still have our 3x squared here, minus 2x plus 3. And then distributing that minus sign, we get positive 2x squared, positive 4x, and minus 5. Now what we want to do is combine our like terms. So those are terms that have the same variable and same power. So for example, we have our 3x squared and our 2x squared. Those are like terms. Then we have our minus 2x and positive 4x. Those are going to be like terms. And lastly, we have these two constants here, our plus 3 and our minus 5. All right, so we'll take 3x squared plus 2x squared. So we get 5x squared. And then we'll take minus 2x plus 4x. So that's going to be positive 2x. And then we have positive 3 minus 5. So that becomes minus 2. All right, and that is our answer. And this is also our polynomial in standard form. And we want to write our polynomials like this, essentially in decreasing order according to the powers of our variables. So we start with our 5x squared, then our 2x, because this has only power 1, and then our constant minus 2. Okay, now we'll look at an example of multiplying polynomials. So we'll look at this example here. And in the previous example, I called the polynomials trinomials because they have three terms. So in this example, this polynomial here is called a binomial because there are two terms. So we're taking this binomial and we're squaring it. So we're multiplying it by itself like this. And what we'll do is use the FOIL method here. So that is this here, and it stands for first, outer, inner, last. And so that's how we are going to distribute our terms. So we'll start with the first terms, our 3x's here. So that's our first. Then our outer is going to be our 3x and our 4y. And then our inner is our 4y and our 3x. And then our last terms are our 4y's. So that's exactly how we're going to distribute each terms and multiply it out. So we have 3x times 3x, so that is 9x squared. Then we have our 3x times 4y, so that's 12xy. And we again have our 4y times our 3x, so that is another 12xy. And then our last terms are 4y times 4y, so we end up with 16y squared. And then again, combining like terms, we only have one x squared term, but we have two xy terms here. So combining that, we get 24xy, and then we only have we only have one y squared term, and that is 16y squared. All right. Now we'll get into some examples of factoring. There are quite a few methods to factoring, and those are in your textbook, but we'll go over some examples to solidify these concepts. So the first one is our GCF method, or our greatest common factor method. So we'll look at this example. So we're given this polynomial here, and looking at the greatest common factor of each term, we see that is 12. So what we want to do is pull a 12 out from each term here. So we're left with x squared plus 2x minus 3. All right. We can factor this further. We can factor this inside here, this x squared plus 2x minus 3. And what we'll do there is we'll do kind of a guess and check method. So this 12 stays out here. And we know that this first term is x squared. So we know we're going to have an x here and an x here. So when we multiply that back out, we want to get x squared. And then we want to find two numbers such that when we multiply them, they equal -3, and then when we add them, they equal +2. Well, the only numbers when we multiply to get 3 are going to be 1 and 3. And then our signs here are going to be determined by what signs we want here. So we know that we need to get a negative when multiplying, so we need to have at least one negative. So I'm just going to guess that we're going to have a -1 here and a +3 here. And we can check this because we know that +3 minus 1 is equal to +2. So we know that this is, in fact, our answer, and that's this polynomial fully factored. All right, the next method we're going to look at is grouping, factor by grouping. So we'll look at another example, which is the following. All right, so first we'll look at, we will literally group these terms. So we'll group these two terms here, and then these guys here. So factoring our m cubed plus 3m squared, we know that we have an m squared term for both. And then pulling that out, we end up with m plus 3 there. And then similarly for our -9m minus 27, we know that we have the greatest common factor here is going to be 9, so we have a 9 in both terms. And pulling that out, we get m plus 3 here, because we pulled out that negative. So we end up with m plus 3 here, and then m squared minus 9 here. Now something to note here is that this right here is called a difference of squares. Since we have m squared minus 9, which is the same as 3 squared here. And in our book, we know that that can be rewritten. So this m plus 3 here will stay here. And then our difference of squares comes out to, well, we know the square root of m squared is m. So we'll have m here and m here. And then this is a difference of squares. So we know that we have a square root of 9 is 3. And since it's a difference of squares, we're going to have one positive and one minus term. All right, and then lastly, we do have two m plus 3 terms here, so we can write this as m plus 3 squared times m minus 3. And that is our fully simplified factored form. All right. The next case we're going to look at is when we have a perfect square trinomial. So let's look at this example. So again, we have a trinomial. There's 3 terms here. And this is essentially exactly the form that we have for a perfect square trinomial in our book. We have our x squared term here, our minus 2xy, and our plus y squared term here. The only thing is that we have this 4 in the front here, but we know that the square root of 4 is 2. So this actually is a fairly simple one. So again, 4 squared is 2, and x squared is just x, so we get 2x and 2x here. These guys will multiply to get 4x squared. And then we also know that our y squared, the square root of that is just y. So we end up with y's there. And then this is a positive y squared, but we have this minus 2xy here. So we know that we're going to have both minus signs here, because negative y squared times negative y squared is equal to positive y squared, which is exactly what we want. And then fully simplifying this, we get 2x minus y squared. All right. So yeah, the main thing to be careful with here is just our signs, but we always know that if we have a minus sign here, that we will have at least one minus sign here, and then this positive sign gives it away, because we have a negative times a negative is always going to be equal to a positive. All right. Next, we want to look at the sum of cubes. So when we have this case, it's usually of this form here. So we just have a sum of two cubes here, and this can be factored to this form here. So we'll look at an example. Say we have 8x cubed plus 216. All right, so this can be rewritten as 2x cubed plus 6x cubed. So you have two terms that are perfect cubes. And looking at our form here, we have this x cubed and this y cubed. And written like this in our example, our 2x here is kind of like our x here. And then our 6 is kind of like our y here. Kind of think of them as placeholders in a sense. So just by thinking of it in that sense, we know we're going to have a binomial times a trinomial. So let me make this a little bit bigger. Right, so we have this binomial times our trinomial. And we know that we're going to have our x term plus our y term as our binomial. And remember I said our x term here is like our 2x. So we have our 2x there. And then our y term is going to be 6 here. So we have 2x plus 6. And then, actually, before I do that, I did want to tell you guys about this mnemonic device for perfect square trinomials. And that is what's called SOAP. And so what that means is this is going to be the same sign. This is going to be the opposite sign. And this means always positive. So this will help us easily determine the signs for these examples. So this means this sign's going to be the same as our original. So this is going to be a plus here. This sign here is going to be the opposite. And then this here will always be positive. So this is always the case when we have a sum or a difference of cubes. So if we were to have a difference of cubes here, then we would have the same sign, so this would be minus. We would have the opposite, so this would be plus, and this stays. This is always positive. Okay, so now that we've established that, let's go back to looking at our terms for our binomial. So again, our x term here is going to be 2x, and then our y term is going to be 6. So our binomial is 2x plus 6. Now in our trinomial, our first term is x squared. Remember our x in this case is 2x. So we want to take 2x squared, and that ends up being 4x squared. Then our second term is x times y. So we'll take 2x times 6. So we get 12x. And then for our last term, we'll take y squared. Our y term is 6. So that'll be 36. All right. And this is our answer for this one. So pretty simple. When you have a sum of cubes, I recommend just rewriting it in this way so you can kind of see exactly what our x and y terms will be in our factored version. All right, so the next case we're going to look at is when we want to factor with substitution. So this is helpful when we have somewhat of a messy looking polynomial. Let's look at this example. Let's say we're given this here, and what you could do is you could do x plus y times x plus y, FOIL that out, distribute this 7 here, combine like terms, and see if this can be factored easily using any of the other methods we've talked about. But what we're going to do instead to make our lives a little bit easier is we're going to substitute a value called t, and we're going to make that equal to x plus y. So when we do this, all we're doing is plugging in t wherever we see an x plus y. So we end up with a polynomial t squared plus 7t plus 12. Now this is much easier to work with, and this is an easily factorable polynomial. So we have t squared, so we know we're going to have a t here and a t here, and both of these terms are positive, so we already know that we're just going to have positives there. And we want to find two numbers that multiply to 12 and add to 7, and that is 3 and 4. Yeah. Now, what we want to do, since we said that t was equal to x plus y, we want to substitute t back in. So we're substituting x plus y everywhere where we see a t. So we get x plus y plus 3, and then x plus y plus 4. And this is our final answer. So not too bad. Substitution definitely helps when you have somewhat of a complicated polynomial that looks like this. And then our last example for this video is the following here. We want to factor x squared plus 12x minus 16. And so we'll try to factor this just by guessing and checking. So we have x squared term here, so we know we're going to have x times x. And this here, 16, is a perfect square, so that kind of makes me want to try 4 and 4 here. However, we know that whatever numbers are here need to add or subtract to be 12x. So no matter what signs we put here, we're never going to get 12x there. So that doesn't work. What we could also do is we know that we could start off by just looking at this term. So we could try 7 and 5, we could try 10 and 2. So let's try 7 and 5. But we know that these numbers will never multiply to be 16. And similarly, if we were to try 10 and 2, those numbers will never multiply to be 16. So then you might be thinking, okay, so what else can multiply to be 16? We know that 8 and 2 can. However, if we were to, no matter what signs we were to put here, we would never get that they would add up to 8. Add up to 12 here. 8 plus 2 is not 12, 8 minus 2 is not 12, and so on and so forth. So at this point, we've essentially exhausted all possibilities, and we've come to the result that this polynomial cannot be factored. And that's okay, not every polynomial is factorable, and if you run into this case on the homework, we would call this prime. This polynomial is prime. And this is a rare case, so you might not really see it on the homework. If you do, then this is what you would answer, but please don't put prime for every polynomial because, like I said, you might not actually see that on the homework. Well, all right, that is it for this section.